Okay, so let's try to consider the function f of x minus z equals to 1 over square root of x squared plus y squared plus z squared, which is 1 over the distance to the origin in 3 dimensions. So to write in a exponential format is x squared plus y squared plus z squared to the power minus 1. The purpose of this problem is to calculate the following expression. The Laplacian of f will be d squared f over dx squared plus d squared f over dy squared plus d squared f over dz squared, or fxx plus fyy plus fdz. Okay, so let's take it easy and start with f sub x. F sub x apply to this expression by using the chain rule. This will be minus 1/2 times x squared plus y squared plus z squared to the power minus 3/2 times x squared plus y squared plus z squared prime, which will be prime sub x, which will be 2x, and eventually we get simplify with a 2 minus x times x squared plus y squared plus z squared to the power minus 3/2. Okay, this will be followed naturally by f sub xx, the second order partial derivative, which will be obtained by applying the product rule to this expression and incidentally the chain rule again. So this will be minus x squared plus y squared plus z squared to the power minus 3/2. Okay, minus x times minus 3/2 times x squared plus y squared plus z squared to the power minus 3/2 minus 1 will be minus 5/2 times the derivative of x squared plus y squared plus z squared with respect to x, which will be 2x. So let's simplify whatever we got so far equals to minus quantity x squared plus y squared plus z squared to the power minus 3/2. Okay, so divide this 2 with a 2, minus and minus a plus 3x squared, right? Because we have 3xx and we have minus here, times x squared plus y squared plus z squared to the power minus 5/2. Okay, let's simplify this. So one of the two exponents to the power minus 3/2, we get to the power minus 5/2. So let's take this to be the ground state, so to say, and give it as a common factor forcefully. So this will be minus quantity, will be x squared plus y squared plus z squared to the power minus 5/2 times we have a 3x squared from here. Then from the other term, we have an extra minus quantity x squared plus y squared plus z squared. So we get minus x squared minus y squared minus z squared, which is x squared plus y squared plus z squared to the power minus 5/2 times 2x squared minus y squared minus z squared. So let's write down from all this computation, summarize what we got. So we got f sub xx after all this computation, we got f sub xx equals to x squared plus y squared plus z squared to the power minus 5/2 times 2x squared minus y squared minus z squared. Okay. Now, let's look at the initial formula, function. X squared plus y squared plus z squared to the power minus 1 half. So, notice the symmetry among the variables x, y, and z. So, x, y, and z are on absolutely equal footing. So, given that x, y, z are on absolutely equal footing, if the second derivative f sub xx of this expression, this part is symmetric. So, if differentiating twice with respect to s leads us to this expression, 2x squared minus the sum of the two other squares, and since y has absolutely the same role as x, playing a symmetric role, we have the same constant, the same factor which is symmetric, doesn't change, x squared plus y squared plus z squared to the power minus 5 halves, times 2y squared minus x squared minus z squared, because y plays the same role in f sub y as x plays in f sub xx. This is a consequence of the symmetry of the problem. And similarly, f sub z equals to x squared plus y squared plus z squared to the power minus 5 halves times 2z squared minus x squared minus y squared. Again, 2 times the variable squared minus the sum of the squares of the two other variables. So every variable behaves in the same way due to the symmetry of the variables. And if we add together those three qualities, we get the Laplacian of f is fxx plus fyy plus fzz times, which is common factor x squared plus y squared plus z squared to the power minus 5 halves times, what do we put here? 2x squared minus y squared minus z squared plus 2y squared minus x squared minus z squared plus 2z squared minus x squared minus y squared. Let's see what we got here. We got 2x squared minus x squared minus x squared. So we got rid of x's. 2y squared minus y squared minus y squared is a 0. They simplify. We got rid of the y's. And finally, 2z squared minus z squared minus z squared. Everything goes. So this will be 0 here. So everything times 0 is 0. So we just prove that the Laplacian of f is. So this will be a harmonic function of in 3 dimensions. What about the one in 2 dimensions? Very similar one. In 2 dimensions, we have the function f of x and y equals to natural log of the one of the two polar coordinates in the plane, which is r, where r equals to square root of x squared plus y squared. So the function f of xy is logarithm of square root of x squared plus y squared. It's a harmonic function in 2 dimensions. So f of xy equals to a logarithm of square root of x squared plus y squared, which will be 1 half logarithm of x squared plus y squared. As before, let's calculate f sub x. F sub x is 1 half times, use a chain rule here, times 2x over x squared plus y squared. From the chain rule, 2 to simplify, we get an x over x squared plus y squared. F sub xx, if we continue, we'll try the quotient rule, so we get x squared plus y squared minus x times 2x over x squared plus y squared squared. And this will be y squared minus x squared over x squared plus y squared squared. Okay? Now, again, because of the, by analogy, since x and y in the original formula for f of x and y play absolutely symmetric role, f sub y equals to x squared minus y squared over x squared plus y squared. So now from these two relations, we get f sub xx plus f sub yy equals to the same denominator, but at the numerator of x squared minus y squared with y squared minus x squared is 0. So the Laplacian of f equals to 0. So logarithm of r is a harmonic functions in